Hi everybody, my name is Blake Corder. I'm here to talk about what we're doing at nTopology. I want to apologize on behalf of Brad, our CEO. He had intended to be here today. The title is a little different with the presentation, but Brad is at customer training today, training a customer. And I'm based in Boston, so I'm here, but it's a pleasure to be here. Let's talk about what's going on in advanced manufacturing. And by advanced manufacturing, I mean mostly additive, but also some traditional technologies are coming along. Today, we can produce parts of incredible complexity. It's no secret. People have been happy about 3D printing and additive because of this potential for unlimited geometric complexity. But it doesn't mean that it's free. First of all, there's a whole new world of material properties that we can explore. We can engineer new material properties. We can control those properties locally at different places within a single design, and we can vary designs from part to part, so each part is somewhat unique. That's just the beginning. Well, if you can even get past the geometric complexity, and by the way, what you're looking at is this is a heat exchanger off of a Airbus 321. The engine's a CFM 56. So 3 of these go around. It's an intercooler for cabin air. So to get the cabin warm, you take bleed air off the turbojet and you shove it through one of these. This is not the one that's on that engine. Of course, we made this just a few weeks ago with our friends at Velo3D. I showed it off at IMTS. The parts are also on our bench if you want to take a look. It's a sizable part, but first of all, looking at this, the geometric complexity is not something that you can represent in any traditional CAD system. Even the emerging systems that are capable of doing implicit modeling, which we'll talk about later in the presentation, we've achieved a new order of magnitude of detail that we can represent in this type of technology, but you can't do this in a traditional CAD system. What if you want to simulate it? You want to do CFD through there. You want to do structural analysis. Your traditional tools are not going to work, especially those that are integrated with most CAD systems. Very high-end simulation technology can tackle it, but your traditional tool chain falls apart. And then there's one even more challenging issue, which is you're building these parts up layer by layer. When you're machining a part out of aluminum, you can be pretty sure that when you're done, you're going to have aluminum left over. Or if you're injection molding a plastic part, you can screw things up with temperature and pressures a little bit, but you're going to put the plastic mostly into the mold. And so those processes have been relatively straightforward, and over the past 100, 200,000 years, whatever it is, we've gotten in control of those processes, but now we're doing something different. Since we're creating the part layer by layer, we're in a much riskier situation. It's not that this is a new engineering challenge. What's happened with composites over the past 40 years to now we have airplanes that are composite shows that we are capable of additively manufacturing structures and making them performant through a life cycle, but it's a much more challenging problem than before. So let's take a look at where the opportunity really lies and what tools are needed to solve it. In the traditional process, you kind of have two things. I'm going to pick out a material, and I'm going to pick out a shape. So you go to your materials library, and you grab your material, and you go to your CAD system, and you make a shape, and then you design it for manufacturing, and you get those shapes with those materials. And it's a fairly, that's what we go to mechanical engineering school for. It's a degree-worthy endeavor. But now there's the introduction of the Mesoscale. I don't really love the word, but it's the right word. And we can now play with we can now modify the geometry in a way that it's big enough that we can manufacture the shape, but it's small enough that the bulk properties are homogenized up. They're abstracted away. We think of it as the material properties that our thing is made out of, not as the material itself. So we've got this weird crossover land. And the size scales here are very approximate. There's some company on Facebook that's been trying to sell me a purple mattress that's made out of this stuff, and it's much bigger lattice than this, but it's still the same idea. We're using this sort of mesoscale structure to give ourselves all sorts of new potential. And there are a lot of structures and a lot of opportunities there. So these are Ashby charts. I don't know if everyone in the room is familiar with them. I find them kind of fascinating, but it helps you see here as a function of modulus, as a function of, or sorry, modulus and strength as a function of density. There's the third view as well. You can see that the materials we have available to us today are segregated into different islands. And what the mesoscale allows us to do is engineer new materials that blur the boundaries of those islands. So what tools do we have, or what things might we want to vary about parts? Well, there are the local properties. What's the modulus, my elongation at break? There's a lot of cool things you can do with Poisson ratio. Again, negative Poisson ratio, so things stretch and expand all the way out, which can have some very desirable properties, especially when you have expansion going on. Vibration damping is a very exciting opportunity. You know, we think of, you know, you listen to your stereo, you have a graphic equalizer, you can just turn up or down a certain frequency that you want more or less of. As mechanical engineers, we're all familiar with resonance problems. There are a number of techniques we can deploy today to make your material a graphic equalizer for your part. Oh, you get a resonance problem around 400 hertz? We'll just make a new part and we'll turn it down there. A lot of electromagnetic applications, defense applications, radar bending applications. And then, of course, these things all stack up to the bulk properties. A lot of our customers, hey, we're putting this part on a satellite. We really care about where the center of mass is. Okay, we'll put the center of mass where you want it. So understanding the displacement under load to be in a specific place. So there are a lot of control that you can add to the process for just the bulk properties. All right, well, how can we make these things? What technologies are available? This list is a sort of a short list of the most fit technologies for manufactured parts. I'm not talking about prototyping. 3D printing, additive manufacturing has a wonderful application in prototyping. This isn't that. These are parts that are going to approximate a shape for the purpose of a validation exercise. These are parts that have a job to do. So you have the metal technologies that are coming along. Polymers are quite mature. But even traditional techniques like CNC machining, at the right scale, you start to think of the work you're creating, the lattices that you're creating more as the material themselves. So this type of thinking that goes into this process can happen with a variety of different technologies. And I just sort of bring up some pretty images. This is a hand-built sculpture. It has 55,000 welds. It's a 40-foot tall sculpture. But when you look at what something like this is made, what you see is different size beams. You see bent beams. You see a lot of structure coming out of the way this was created bottom up. And it looks right to us because we're used to seeing organic things that are generated from the bottom up. I think it's one of the reasons topology optimization is inspiring as one of the ways of doing generative, because it feels very much like it grew out of nothing. But you can also do this type of process top down. So while this is maybe not really advanced manufacturing or a practical application, it shows the idea that you can, that these structures naturally do form and are clearly optimal. So what is this family of, how do we make these materials? What are they? You know, when we learn material science, you learn about body-centered cubic and face-centered cubic and the different types of crystallographic structures that are available for materials. Well, we have all of those in sort of beam-type structures and more. So what I'm trying to show in this diagram is on the horizontal axis goes from open cells to closed cells. So if you have a powder bed kind of process, you need to make something that's at least open someplace so you can shake all the powder out. There are other technologies like FDM that can do closed cells. And I can tell you from the bleeding edge of academic research that it's pretty clear that if you can make closed cells, you're going to create higher performance, at least for strength, for strong lightweight parts. You're going to do better with cellular models, honeycomb-type models, than you will with open beam models. However, there are very few technologies that can make industrial strength closed cell parts. So then in the vertical axis, there are a number of technologies that are ordered where the structures are periodic. The top one, TPMS, triply periodic minimal surfaces. Gyroids are one of the popular ones to use. It turns out diamonds are a little bit stiffer than gyroids. We're just finding out they were excluded from some early research. So if you're making lightweight structures using gyroids, you probably want to rerun your stuff using diamonds. Schwarzes are out there. They're better at compliance. Then you have the periodic structures, lattice structures that repeat over time, over space. But as you go down the stack, what you start to realize is that a truss structure and a honeycomb structure are self-dual. So there's a set of techniques you can use to create one or the other. They don't really mix very well in structurally interesting ways. And then there are the more stochastic and random approaches. We can certainly take all the 1980s graphics tricks like Perlin noise and whirly noise and deploy those to making nice textures. A lot of good reasons to do that for aesthetic purposes, also a lot of good reasons to do that for medical. And also, if you want to have a structure that has no resonance whatsoever, random patterns are better at that. And then there's other kinds of sort of just random shape noise. Instead of using a graphics technique, you can just throw millions of little rods at something. And if you have the right modeling kernel, that's no big deal. So this is the domain in which we have to play. Okay, so you get all that understood, and now you finally go out and you buy yourself a metal printer, and and now it's your job to start to get parts out of that and get your organization centered around it. And maybe it starts as a research exercise, but no one bought that machine for research. They want to make parts. Okay, so most metal technologies, there are some that are promising better results, including partners of ours, but the reality is that you're going to make a lot of bad parts when you get started. You're going to find out that environmental factors can affect what you're doing. Humidity, for example, can make, one day you produce a good part, the next day is totally different properties because of a change like that. You wouldn't believe what can mess up these laminated objects. I can tell you a story of a company that bought a machine and they put it in an office building, and they noticed that every once in a while the layers were getting messed up. Just up the build, just every once in a while, for a little while, the layers would be all messed up. And after a little while, they realized that that was happening during rush hour. And then they actually got a seismometer and realized that what was happening is that this was an office building with a parking garage in the basement, and as the cars were coming and going from the parking garage, it was making little vibrations in the building, and that was messing up the parts. So you don't have to worry about that when you buy a CNC machine. It's vibrating enough as it is. Okay, so there's the process issues. Now you got to get your team using it. And certainly you can print CAD parts. They're going to warp more than maybe the latticey ones, but you can print some CAD parts. But that's not really why you bought the machine. If all you're going to do is make normal CAD parts, you probably could have CNC'd them or cast them. So how can you equip your software team to actually take advantage of what you have? We already covered the fact they can't model those complex geometries in their CAD system, and they probably don't want to change their CAD system. So how can we give them all the benefits of this advanced manufacturing stuff without really changing their process too much? So I just want to take a step back and add up those last slides. Some of those I realized had a lot of bullets on them, and there's a reason. It's to set up a little bit of math, and you can run the numbers on your own. This is just based on my seeing what's out there. There are about 20 different types of machines that make things in different ways. There are about 20 different kinds of structures, let's say, that you can use to do this mesoscale latticing work. There are about 20 properties that you might be interested in taking a look at. They're tied to each other, but you might be more interested in compliance than, say, stiffness. Usually those are opposed to each other. Then you've got the actual materials you load in your machine and all those process considerations I talked about. So if you wanted to claim that you really understood the landscape of additive manufacturing, you would have to understand a million different ways of putting things together. That's how the combinatorics work out. No one will ever do this. You will not go to school and learn all of this stuff. There's something else going on. And just to be explicit, if you look at one of our kind of standard design through manufacture processes, I realize the gentleman from Autodesk got a much prettier chart for a design through manufacture process, but we have a couple different activities. We have a design activity in green. We have we have a manufacturing activity in pink. We have the simulation activity in blue. And detailing and validation is where you most depend on your CAD and simulation tools to do a job for you. Well, in the advanced manufacturing world, the core center of those, everything except for maybe PLM, is not the best tool for the job and will not get you the best results, and it's going to fall over on itself. And we have customers who spend 8 hours letting something regenerate in their BRUP-based CAD system, and they model up in our system, and they can do it in a half hour, but the actual building, the calculation of it just takes 15 seconds. So you definitely need a different tool to do it. And meanwhile, you have new tools that you need to bring into the process. We're going to be worrying about infill selection, even if you're just doing prototyping. You have to worry about your design allowables with those material properties and your manufacturing allowables with how many you can actually produce. Those are measures of how many standard deviations of quality you need to have in manufacturing fitness that are used in aerospace. Support synthesis, where does that fit into everything? So you have these new deliverables, and your old tools don't work. So you're really off in the Wild West. The good news is we're all familiar with an industry that's used to dealing with this level of complexity. In fact, John Hirschtick, for years in the early days of Onshape, was giving this wonderful presentation about how making web software is like jazz. And if you didn't see the presentation, I'm not going to go into it now. But John, if I could summarize it, basically made the point that in the old days of making software, you buy Visual Studio and you just did everything there and it was fine. But nowadays, there are so many different tools. You're taking all these little hipster, like programming systems of JavaScript and pulling them together into an ecosystem that's your own, and you're designing it and engineering it. And so it's a much more fluid environment. And what we've learned in the software industry is how to survive in that environment, how to build quality products in it. And there are 3 lessons from software engineering that directly apply to advanced manufacturing. So the first is to lock it down. Mostly we think of that in software as you check in your code with a test so that no one else can break your code because the test will be there to let them know. And that's one version of it. Another kind is if you're making a new product, a new prototype, maybe something with a server on the back end and a client front end, what most engineers are tempted to do is take the team and say, okay, you work on the server back end, I'll work on the server API, and then you work on the client API, and then I'll work on the client code. And split up into little pieces and give each piece to a different member of the team, and then at the last minute try to integrate everything. That's a terrible idea in software. What you usually want to do is get everyone working together from the beginning and create a single thread, like a hello world that goes all the way from the server to the client, so that you know that's working, and that the most tested part of your code then becomes the integrations between the components, not the components themselves. And that's very much the case of what needs to happen in advanced manufacturing. You need to find one lattice structure, one material, one printer, one set of process conditions, and get that working end to end from your CAD users all the way through to your manufacturing hardware. And once you've got that one working and you're making parts and you've paid for that machine, then get your next process working. And I think it's unusual for mechanical engineers to think that way, but you do have to think a little bit differently. And then the third part of the culture is ship it. I guess the cat's out of the bag. I used to work for GrabCAD. At GrabCAD, we would ship software. We would deploy software live to the internet several times a day. Merge to master, that's it. And the reason is you just want to keep moving. You've created the value. You want to get that value to your customers as soon as possible. And in the same way, if I'm a manufacturing engineer, and I figured out finally how to get good parts out of my machine, my job is to ship that to my engineers so they can start making parts and using the process I just built for them. If it's all tied up in my little corner of the world, no one's going to use it, and that's wrong. So how do we do it? Let's take a look at some gyroids and some Schwarzes. So these slides, I didn't put a message on. These came from AFIT, the Air Force Institute of Technology, that are working with them. So we got some, they're doing exactly this process now. They're validating a number of different configurations of a couple different lattices to get them under control. They're printing them out on their fancy machines. And then they're locking it down. So what you're seeing here is some thermal imaging. You're seeing some simulation. This simulation came out of our software, but it's being done in Abacus. We have great solvers for doing the lattices in our thing, but for validation, for the really advanced stuff, the stuff Jing was talking about this morning, we also have integration with ANSYS. You're going to want the really high-end tools to do a little bit of that validation just the once. Whoa. Step 2, automate everything. So here is a part in our new product, nTop, along with the slicing for it. Usually the path, by the way, to go to manufacturing, especially for complex geometry, we're not using the STL anymore. It's great to do your model setup on BREP, and you can for the technologies that you can, but at some point, we're just going to produce the slices. Our customers would run into they're slicing triangles. It's just not worth it. And we're not the only ones who are doing this, but it's just sort of the reality that the main thing we're going to deliver is going to be some slices to the CAM system, and maybe a mesh or a simplified parasolid model back to the CAD system so the CAD guys can see it in their context. But the real deliverable is usually slices. And so the point being that you need to automate that by creating a single workflow where it just happens, and then you ship it. And this is the most magical part of our new software. I'm not going to spend a lot of time on the software, but the basic idea is that once you've gone through the process of setting up these materials in our system and you understand the properties of lattice and you've got it validated, that becomes a reusable thing. And we can take that knowledge, the homogenized information about what the bulk material properties are, and give that as kind of a workflow template to the rest of the CAD team. So every CAD user, once they've produced a multi-body model that expresses their design intent, can just process that with our tool like a batch command, and it produces perfect manufacturing deliverables exactly the way the manufacturing engineer did it. So the manufacturing engineer becomes an IT guy. Think about it. We're controlling the material properties through software, and the person who's sitting there by the 3D printer has figured out this process, and he's now delivering tools to the rest of the organization so that it can use it. It's really more like an IT model than your traditional manufacturing model, where the designers are supposed to know what's going to be made, to follow the rules so that the manufacturers can make it. In this case, you're creating the automation for the CAD team from CAM. To me, this seems like a very different way than most people are used to thinking of, but this is the only practical way to make use of these tools. So we have a bunch of customers doing it, a lot of name brands. I'll tell you about 2 of them. So ANSYS is making medical devices for the spine implants. They sort of go where your vertebral discs go. And I love the way Asher, our customer, talked about the experience of using our product. Rather than telling your software what to do, you tell the software what it needs to do, and the software then tells you how to do it. That's really what we're trying to do. What some might call this functional modeling. We like to call it computational modeling. Lockheed Martin, big customer. I can't tell you what they're doing with it, but I wanted to say 2 things. 1, they've invested $2 million in our company for a reason. And 2, if you look at the F-35 parts here, you'll notice that these are a lot of machined bulkhead kind of components. These parts are good examples of advanced manufacturing where subtractive manufacturing, the design of these parts can be a lot more like the sort of functional modeling we're talking about. It's a forward-moving process as opposed to an iterative optimization process. So the same rules apply to this kind of manufacturing as to additive, except the material is going to be okay in the end. So with that, we have a new product. It's in private beta right now. We're doing pilot programs with large customers. If you're interested, let me know. It's the next generation of our software. You may be familiar with our Element product. And our Element product, I think, is pretty well known as the best-in-class lattice design and advanced manufacturing software. But we've created a new product for a couple of reasons. 1, the process stuff that I was telling you about, the ability to create these reusable workflow templates to share them with the team and make that part of an automated process. We needed a new architecture to do that well. And we also took our knowledge from the first version of our implicit kernel, and we made a new implicit kernel. And I like to say that it runs on infinite impossibility drive. If you're Hitchhikers fans, you might know what that means. I won't explain it to you right now, because Martin's looking at his watch. But we have an amazing modeling kernel that can do things that I'm not aware of anything else in the world that can do it. It's our own. So we've created a new implicit modeling kernel that can handle complexity at a level that other implicit kernels cannot, in our belief, but we haven't. It's a new field. And the benefits of implicit modeling, quite briefly, are that things never fail. So if you've ever used a CAD system and it said, hey, I can't round that, I can't off that, I can't draft that, those problems don't exist anymore. And so if you want to do things like round 1,000,000 beams to each other, you need a technology like this. It also allows us to work directly with topology optimized code. We can sort of bring anything in and produce good results. But we'll begin to have a kernel conversation another time. So thank you all very much. I hope you got a little insight about what our business is about at nTopology, that we have a new product that lets you integrate these things in an enterprise framework. And I really appreciate your listening. So cheers.